Okay, let's pick up where we left off last time. And uh, maybe I should back up and sort of dovetail it. We had finished talking about uh, how to write reactions, and these are double displacement reactions. And most of the double displacement reactions involve solution chemistry, stoichiometry, and the production of a solid, a precipitate. The production of the precipitate is what drives the reaction. Because when we mix something here with something here, at first we've got cations, and anions here, and then let's see, let's make this one up, A and B. Cations and anions, and each one of them, they're soluble. When you mix them together, now this anion has a chance to interact with that cation and vice versa. And if a precipitate is formed, then one of these pairs produces a solid. And when that solid drops out of solution, that effectively removes most of it from the reaction environment, which drives the reaction toward the products. We'll talk about that in more detail and actually how to quantify that type of reaction solubility in those terms in the second semester. So right now we just want to look at, well, we're jumping off from this point. So we describe the complete reaction as an ionic mixture. So we draw the ions out of the formula equation, and then we look for spectators, those that actually don't participate in the reaction. And we cross those out, and that gives us the net equation. The net equation describes where the action is in the reaction, the action of the reaction. Now we're going to go ahead with stoichiometry of these solutions, because now you've got the balanced equation, right? And I've given you all the tools for balancing these equations. Now we're going to go to the stoichiometry of solution stoichiometry as an extension of what we learned already about general stoichiometry, where we usually have solids and gases that were our examples. All right, these are just step-by-steps. It's going to be easier to describe if I just give you an example. But there it is in green letters, almost green. They're green on my screen. They're kind of light green on yours. And there's that chart I mentioned. This is the solubility chart. When you interact a cation with an anion, you can tell if it's likely to be soluble or insoluble. And for now, we're going to speak in terms of absolutes. It's either soluble or it's not soluble. And in the second semester, we find out, there's kind of a gray area in there. It's a continuum. Even the insoluble compounds are slightly soluble. I mean, very slightly soluble. So for now, we're just going to approach it this way. If the interaction gives you an open cell, then it's soluble. If it gives you a gray cell, then you can consider it insoluble, forms a precipitate. And there are some examples. There are some examples in there that are unstable. And we see those asterisks in there. You look down at the asterisk, the 3 asterisks, most of the oxides of group 1 and 2 react with water to form hydroxides. So even though you get the oxide, it doesn't stay very long. It reacts with water. That's one thing that we have to keep in mind, is the solvent could be a reactant. Right? If you ever throw a chunk of, say, sodium, that's a big chunk. Potassium works better, but sodium's okay. Big chunk of sodium in your neighbor's swimming pool, it'll blow a hole in the bottom because it reacts with the water, right? Produces hydrogen gas. And big enough chunk, you'll have these hydrogen bubbles coming up. It's going to expand really fast. That's what cracks the bottom of their pool. And then when the bubbles reach the air and mix with oxygen, there's enough heat there. It's an exothermic reaction. There's enough heat to set it off, and you'll have this flame coming out of the water. Like I say, potassium works better, but sodium's easier to get hold of. And disclaimer, I didn't tell you to go do this to your neighbor's pool. Okay. All right. You can do it to your own pool if you want. And then magnesium sulfide, the 2 asterisks decomposes in water. So even though the magnesium sulfide is soluble, it decomposes, so it doesn't stick around for long. And then the single asterisk was calcium and strontium hydroxides are classified as slightly soluble or even soluble in some textbooks. So there's a gray area there, and I avoid those simply because there's too much controversy. So there's no need in muddying the water at this stage in your career. All right, so here's an example of a word problem where we're given conditions. We're saying we have 10 milliliters of a solution of sodium phosphate, 0.3 molar. And we combine that solution with another solution that's 20 milliliters of 0.2 molar lead-2 nitrate. And we say, all right, what happens? First thing you have to do, since these are names of compounds, you got to write the compounds from those names, right? That's why stoichiometry was so important. Sodium phosphate. So we know we have sodium and we have phosphate, which is a polyatomic ion. And you can look it up in that chart I gave you. And that same chart will be on the exams. Right? So it's a 3- charge. Sodium is an alkali metal. It's always +1. So we know to balance this, we need 3 positives to balance that one. So that's why we need 3 there. Okay. And you can assume that it's soluble because we're saying a sodium phosphate solution. You don't even have to look that one up. So we know this was aqueous. Okay. Then the other reactant is lead-2 nitrate. It's a type 2 compound because we're given the charge of the lead. Right. Lead is 2+ in this compound. Right. Usually it's either 2+ or 4+. So 2+ in this case. And the nitrate is like this, and it's a 1- charge, so this has to be 2. And that's aqueous solution also. Okay. So we don't have to have these unless we're going to break it out into ions. But what we can do is we know that this is going to be a 2+. We know this is a 1+. This is a 3-, and this is a 1-. Then you just swap partners. To answer that question, what precipitate will form? We don't need to know yet how many milliliters and what concentration. But to answer the first question, you just need to know that this cation interacts with that anion. Okay, so that's one possibility. We have Pb, and I better put the 2+ here, and then PO4 here. That's a 3-. So now we put the 3 over here and the 2 over there because odds and evens cross multiply works. So we put a 3 here and a 2 here. And then you go look in your chart and see the lead-2+ and the phosphate interact and you get a solid. So there's your precipitate. Now sometimes you can get 2 precipitates. Not very often, but it's possible. In this case, I wouldn't expect it because there's nitrate. All nitrates are soluble, every one. So when sodium interacts with nitrate, plus all sodium salts, they're soluble too. So we know that this one is going to be sodium nitrate, and it's still soluble. So we've got a bead on our spectators. Sodium and nitrate are spectators because they're still soluble on both sides. So to answer the question, there's our there's our precipitate. And let's see, is it animated for the answer? Oh, we're going to go through the whole spiel here. Those are the possible ions in small print. So the precipitate is an interaction of lead and phosphate. Okay, now to answer the second one, we need a balanced equation. So I should have moved this over for, let me do that. Let's move it over here. Aqueous. And then let's put this one. Leave ourselves room for the coefficients. Lead to nitrate. That's aqueous. Now we've got room to put this compound. 2, that's a solid. And then all we got left is sodium nitrate. Okay. Now the next question was, what's the mass of the precipitate if we put these two solutions together? So the next thing I want to do is put what I know up here for the equation. Well, actually, we probably should balance the equation first, didn't we? Okay. Remember the trick. You got phosphate on both sides. You got nitrate on both sides. So we can keep them intact as balancing units. So I count sodiums, phosphates. I'm not going to put the charges in here. It's just for balancing purposes. There's our lead, and there's our nitrate. On this side, we have 3 sodiums, 1 phosphate, 1 lead, and 2 nitrates. On this side, we have 3 leads right down here. And we have 2 phosphates right here. And we have 1 sodium, and we have 1 nitrate. There we go. And we can see that it's not balanced yet. The nice thing about these double displacement reactions is they are generally well behaved when you balance them. So if we start with this first one, which is where I would start, we want 3 sodiums. Right? So I put a 3 here. That gives me 3 sodiums and 3 nitrates. Okay. Now, let's see. I need 2 leads on this side. Wait a minute. No, 3 leads. I need 3 leads on this side, or 2 phosphates on this side. Let's do 3 leads. Because if we do, yeah, let's just do 3 leads here. That gives me 6 nitrates. Okay. Now, I need 2 phosphates on this side. That gives me 6 sodiums and 2 phosphates. And we've got 2 and 3. We've got 6, 6 here and 3, 3 there. That's sodium nitrate. So if I up this to 6, that makes 6 sodiums and 6 nitrates. And we're balanced. I think there's an easier way to get to that one, but it works. I guess this is a good demonstration that there's different pathways to the finish line. But now we've got a balanced equation. 2, 3, 1, and 6 are our coefficients. All right, now we can talk about stoichiometry because we've got a balanced equation. For this, I want to say sodium phosphate is 10 milliliters. Let's see, yes, 10 milliliters of what concentration? 0.3 molar of this compound. And to understand this, you don't want to look at that yet. That doesn't have a bearing on what's happening here. That only has a bearing on what happens when you go from one place to the other. Okay, and we also got 20 milliliters of 0.2. 20 milliliters of 0.20 molar of that compound. Okay, when we put these together, what precipitate's going to, the precipitate we know that's going to form, we want to know the mass of the precipitate. So the next question is, you're given exact amounts of each one. We can tell how much of each one of these we're given at the beginning. Because remember, molarity equals moles per unit volume. So if I solve for moles, moles equals molarity times volume. Okay. So we got molarity and volume, we can find out how much we're starting with in an absolute amount of moles. And once you have moles, you can go anywhere. Now, the next trick I want to give you is when you multiply milliliters times molarity, you get millimoles. And it's easier to work with that than having to change that to liters and go to moles. We don't need to do that yet. Right. So if we do that, 0.3 times 10 is with two significant figures, right? Yeah, just two. So we've got 3 millimoles of this compound. That's what we're starting with. And this one we've got 4 millimoles of the compound. Next question we have to answer is, since we're given absolute amounts of each one, you can bet your last dime one of them's going to run out first. One of them's going to be limiting. We have to find out which one's limiting. So one of the surefire ways is to say, if I take this 3 millimoles and I make this all into that, how much does it give me? But if I use all of this, how much does it give me? And the one that makes the least amount is the limiting one. Okay. All right. So if we're going to go from 3 millimoles of sodium phosphate, we need a conversion factor that will go to this one, precipitate, PO2. Well, this needs to be on top. This is our conversion factor. So it's 1 millimole of this one. And on the bottom, we put sodium phosphate to cancel out. And this one is 2. Okay. So that cancels this one here, and this is 1/2 of 3, which is 1.5 millimoles. That's how much this would produce if we used all of it up.
Why is that? 1, 2.
Did I do that right? 2 into 3 is 1.5, isn't it?
Okay. Or why is it 2?
This.
From there. Okay.
Yeah. These, you make your conversion factors out of the coefficients.
Okay.
We're trying to cancel this one and go to that one. And the ratio is 2 to 1. Okay. All right. So we've done that one. Now let's do this one. This one is going to be that much nitrate. And we need a conversion factor now that'll get rid of this one and leave us with the same one. But this is a different conversion factor because different coefficients. Now this one is 3 and 1. Okay, so this one cancels, and 3 into 4 is 1 1/3, right? So that's 1.33 millimoles of lead 2 phosphate. Okay, now we can say which one is limiting? This one. We'll have some of this left over, but we're going to use all of this to make that much because 1.33 is less than 1.5. Okay, now that we have the millimoles of this, we just need to convert it into mass because this is a solid settled out in the bottom of our beaker, and all we have to do is run it through a filter and stick that filter in an oven and dry it. And we've got the weight, we got the mass. But we're going to calculate what it would be if we got 100% conversion from this one to that one. Right? So we're saying 100% efficiency. That's where we're at now. This is ideal. Okay, so 1.33 millimoles is how many moles? 1.33. If I do this, what does milli mean? Huh?
1,000, right?
1,000th.
1,000.
10 to the minus 3. So why don't I just do this? There you go. There's my milli and there's my moles. So now I can convert moles to grams. I just need what? The molar mass of that compound. So let's see. Get my calculator out. I'm taking a lot of time on this one slide because this is the same technique that you'll use for any one of these solution problems. Let's see, 3 leads. 3 times what? Well, let's see, there's lead right here, 207.21. That's grams per mole, just for the lead. Now we're going to add to it, how many phosphorus? 2. Subscript of 2, right? 2 phosphorus, which is 3097. 3097. And then we have how many oxygens? 8. Yeah. You got 4 inside the parentheses and a subscript of 2. That's 8. And oxygen is 16. Now we can add those together. Let's see. I'm not going to tax my brain. I'm just going to use my calculator. So this one's 128. And then 3097 times 2 is 6194 added on to that. And then 207.21 times 3 added on to that. And I get 811.57 grams per mole. 811.57. 811.57 grams per mole with this compound. It's a heavyweight. Times this value, because the moles cancel and leave us with mass. So 1.33 and then an exponent minus 3. And I get, let's see. Yeah, I tacked on an extra decimal. Would normally be 1.08 grams. Or if we only have 2 significant figures, it'd be 1.1. I'm a little lax on the decimals when we're doing these types of calculations. Let's see. Oh, there's the balancing equations. And there's the calculation of the reactant amounts. Yeah. And then we go to the next one and yeah, go ahead.
Just to be clear on,
Go back.
or no, right there.
Okay.
With where you did the 1/3 of the PB3,
Uh-huh.
like the one on the bottom, that's always the one that's not the observer.
The one you mean talking about this term right here?
Yes, you're always going to divide by.
That's the one you want to get rid of,
Okay.
right? Because the one you start with is in.
My bad, I'm talking about the one on top.
This one?
Sorry. The PB3 PO4.
PO4. Okay.
Yes, so you're always gonna do the one that is the precipitate for this.
Yeah, this is the one that you're going to end up with.
Okay.
And it's the same process as our dimensional analysis with simple unit conversions. That's exactly the same thing. The one you want to get rid of is in the denominator, and the one you end up with is in the numerator for your conversion factor. because the term you're starting with is always in the numerator. If it's just sitting there on one line, that's the numerator.
And you're putting that there because it's asking what mass to precipitate, so you're gonna use that both times.
Well, yeah, you have to,
Okay.
we're, at this point, we're only going from one place to the other.
Okay.
And you have to have moles to do that. So once we got the moles of the limiting factor, now we know the limiting one is 1.33 millimoles. We just convert that to moles. Let's see. And there's the convert. I kind of skipped a step there. There we have 1.33 times 10 to the minus 3 moles is the same thing as 1.33 millimoles. Then there's our conversion factor. I ended up with 54. Did I do a miscalculation here? Yeah, I did. No, this should be maybe 5. Anyway, close enough for government work. I ended up with 1.8 gram, 1.08 grams. I used to be able to say that day in and day out because I work for the federal government. Okay. So now that we have answered that question, this is how much the precipitate is at the end of the experiment with 100% conversion, right? If you don't consider the losses, and the only way you can do the losses and do a percent efficiency is actually do the experiment and measure it. And I guarantee, well, actually, there are 2 possibilities. If you don't dry it down sufficiently because it's aqueous to begin with, you don't dry it down sufficiently, you're going to be weighing water along with it. You know, that's a source of error. So it could end up to be 1.2 or 1.3 if you don't dry it enough. But if you get it bone dry, then you're probably going to have less than 1.08 due to experimental losses, right? You might leave some in the paper. The precipitation may be incomplete, right? You may have significant solubility of this compound that leads to less value of the solid. Okay, now the next question is, what's the concentration of nitrate ions? Well, notice that the nitrates are spectators, right? You've got the same moles of nitrate here as you do there. So what has changed? The moles of nitrate didn't change. What's changed is the volume, because you started with 20 milliliters of nitrate here, and we added 10 more milliliters to it. Now you've got the same number of moles in more volume. You have diluted the nitrate concentration. Okay, so we should expect to get a nitrate concentration that's less than, let's see. Well, this is the concentration of the whole thing. What we want to do is find out how many moles or millimoles, let's just say millimoles. I'm going to show you where I'm headed. Millimoles of the compound is how many millimoles of nitrate. So if we just look at this right here, 4 millimoles of that compound is how many millimoles of nitrate? You've got 2 nitrates for every unit. So you actually have 8 millimoles of nitrate. You still have 4 millimoles of lead because there's only one of them. But we got 2 nitrates, so you actually have 8 millimoles of nitrate. Okay. I see questioning looks. At least I don't see head spinning.
If the whole compound is 4 millimoles,
Yes.
so why would the nitrate, even though there's 2 of the nitrates, why is it more than the total?
Look at it this way. Say we write it this way. We got lead on that side, and we got a nitrate on this side in the compound, and we got a nitrate in this side on the compound. Right? 2 nitrates for every lead. So if we got one of these, we've got one of those. But if we got one of those, we got 2 of these. is twice as many nitrates as it is the whole.
Okay.
Okay? All right, so what we actually have is 8 millimoles of nitrate. Now, that's millimoles per how many milliliters? 10 plus 20. Right? 30 milliliters per 30 milliliters. Millimoles divided by milliliters is molarity. Why? Because milli cancels milli, moles per liter. Okay? So now all we have to do is calculate the concentration. So that's 8 divided by 30 is, let's see, in standard notation, 0.2, let's see, 7 molar nitrate ions in solution. Okay? These are not easy concepts, right? If it's your first exposure to them, right, they can spin your head around backwards. Right? You just have to take it slow and logical. And that's what I'm here for. Okay, now here's a more difficult one. How much phosphate is left in solution? Remember, this is the limiting reactant. This is the excess, which means there's going to be some sodium and some phosphate left over. Well, all the sodium's left over because it's not part of the precipitate. But some of the phosphate is tied up in this, but not all of it, because it's excess. Okay? What we have to do is find out how much is left. We started out with 3 millimoles of this compound. Right? So if we have 3 millimoles of that compound, we have 3 millimoles of phosphate that we start with. Right? So that's what we're starting with. Let's see, let me remove some of this stuff. And we've already done that one, so we're going to use this space for calculations. All right, that's the starting amount. How much did we use? Well, all we have to do is go over here and say, all right, we ended up with 1.33 millimoles of this compound. Right? So how many millimoles of phosphate are tied up in the solid? Right? 2 for 1, right? 2.66 millimoles, right? Are tied up in the solid because it's 2 to 1, 2 to 1. This is 1. Twice that is phosphate. We're good? Okay. So that means we've used up, let's see. Forgot to erase that one. We've used up 2.66 millimoles used. All right, so we have left over, let's see, 4 and 3, right? 0.34. Yeah. Millimoles of phosphate in solution. Okay. So now we can do the same calculation. We know this is in solution. The molarity is just the volume divided into that millimoles. So this is 30 milliliters, just like before. And 30 into 0.34 is what? Well, it's right there on the page. 0.34. Let's see if I get the same answer. I get 1.13 times 10 to the minus 2 molar. If we move the decimal 2 places to the left, it's 0.011. 2 significant figures. Molarity. Okay. Yeah, we answered actually 4 questions out of that one problem. First of all, what's the precipitate? How much precipitate is formed? What's the concentration of the nitrate left over, and what's the concentration of the phosphate left over out of that one problem? But it took multiple steps. And if you get in a hurry, especially on an exam, your mind can just like spin like a tornado and nothing happens. So you got to be very methodical about it in practice. Try to work several of these types of problems before you have to do it in a crunch. Okay. This is a double replacement precipitation reaction. Right? It's both kinds, double replacement and a precipitation reaction. Now we're going to look at acid-base reactions. And this is going to be kind of an overview. We get into, in the second semester, we get into much, much more detail with acid-base reactions. So we're going to try to just work it in terms of stoichiometry. How do you use acid-base reactions to answer stoichiometric questions? And we're gonna stick to this definition of an acid and a base. Right? We'll go into more detail in the second semester. This is a Bronsted-Lowry definition. An acid is a proton donor, hydrogen donor, and a base is a proton acceptor. Okay. So if we have an acid, and this can vary, but most acid-base reactions that you're going to be encountering are this type. They will have, let me use this example. Say you have this hydrochloric acid in solution. You got another solution that you're going to add, and it's a base, sodium hydroxide. Okay. And what that does, and this can be treated as a double replacement reaction. The hydrogen combines with the hydroxide to give you water, right? HOH or H2O. And then the sodium and the chloride combine to give you a salt solution, table salt. Okay, so if we look at this in terms of, this is the formula equation. If we look at it in terms of the complete ionic equation, in solution, what you have is actually protons, right? Most of them are single protons because there's very little deuterium, very little tritium. So you're talking about a single proton. That's really, really small, but it's got a positive charge. And you got these protons in solution. In reality, I'll tell you this, you don't have to worry about it right now, but in reality, those protons never exist separately like that. They're always attached to something. But for calculation and stoichiometry problems, you can write it this way. The math works the same way. And then we have chloride ions, right? And then we have sodium ions and hydroxyl ions. Okay, and this makes water plus sodium ions and chloride ions. Okay, there's your complete ionic equation. And then for the net ionic equation, we just cancel the spectators, right? Take the spectators out here and here and there. So for our purposes, I can say this, all acid-base reactions are hydrogen ions plus hydroxyl ions yield water. That's why that blue statement there. Now, if we look at it in terms of the acid-base definition, which one is the proton donor? Which one gives up a proton? That one right there. That's your acid. And which one accepts the proton? This one. That's the base. Because this part of it right here accepts this part of it and makes that. Okay. And we simplify it to this one. This proton donates itself to that hydroxyl, which is the base, and makes water. Okay, let's see if this is going to work.
Hydrochloric acid contains hydrogen ions and chloride ions in aqueous solution. Sodium hydroxide contains sodium ions and hydroxide ions in aqueous solution. When these two solutions combine, a neutralization reaction takes place. In this reaction, hydrogen ions from the acid and hydroxide ions from the base combine to form water molecules. The sodium and chloride ions are unaffected and remain to form a neutral sodium chloride solution. Neutralization can be summed up by this simple ionic equation.
Okay, so in that animation, I don't know if you noticed it, there were no free hydrogen ions floating around. Right? They were attached to water molecules. Normally water's like this, right? But we've got a place up here to put another hydrogen. And that brings with it a positive charge, right? Because this is positively charged when you add it to the water. Now the water, this is the hydronium ion, and that's the way hydrogen ions always work in aqueous solution. They attach to the hydroniums until they're transferred to something else. Okay, but you don't need to dwell on that right now. Well, that's coming second semester, and we get into much more detail and make use of that. I just wanted you to be aware of it for this semester, and we'll talk about it more next semester. Okay, acid-base reactions. They're very similar to, as far as stoichiometry goes, they're very similar to the double displacement reactions. You want to construct your equation correctly with the compounds written correctly. Then you want to balance that equation, calculate the moles so that you can move from one place to another, and then do that movement, and then answer the question. It may be in terms of grams. Some acid-base reactions produce precipitates. Some don't. They always produce water. So the driving force for all acid-base reactions is the production of water, because water is very stable. It can do this thing. It can go back this way. It's just most of it, it really wants to be this way. Only very small amount goes this way. Right. Okay. So that's one of the driving forces. Producing water drives the reaction toward neutralization. Let's see. Are we going to do constitution law? Yeah, lab exercise 6. We're going to do a titration. So, a titration, it can actually be almost anything you can titrate. What you want to do is take a solution of unknown concentration and compare it to a solution of known concentration by adding them together and having some way to indicate when their molar ratios are equal. Because if they're equal, then you know how much of the known you used, and you can transfer that amount to your unknown to calculate its concentration. That's basically what a titration does. An acid-base titration uses this reaction. Acid-base produces those. And we generally use a color indicator. Like you've seen phenolphthalein before. In acid solution, phenolphthalein is clear. When you go basic, it turns pink. So we're going to use that one. Now the endpoint for this acid-base reaction is when you actually have exactly the same moles of this as that. They're equal. All of this goes over here. That's the equivalence point, excuse me. That's the equivalence point of this reaction. When the moles of acid exactly equal the moles of base. If you're using an indicator, and the only way you can tell this is to use a pH meter and draw your titration curve. But an endpoint is determined by a color change indicator. And that means you can work a lot quicker. And usually if you pick it right, if you pick the indicator correctly, then it changes colors at just the right point so that it tells you when this is happening, when the equivalence point is met. And you're usually not very far off if you pick it right. So our acid-base reactions happen in the neighborhood of mid pH 8s, and that's when phenolphthalein changes color. All right. Let's see how much time. I'm gonna run out of time again. How many more slides do I have anyway? Do I need to hurry? Oh no, I'm in good shape. Yeah, we're good. If we titrate sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide are required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint? Okay, so the first thing you have to do is write your compounds correctly. And fortunately, they're given to us. So our reaction is sulfuric acid in aqueous solution and sodium hydroxide in aqueous solution. And this is reacting to produce what? All acid-base reactions produce two things: water and, chemically speaking, the salt, which would be a combination of sodium and sulfate. Because if you use hydroxide and hydrogens to make the water, the only thing left is sodium and sulfate. Right. So this is water, and this, chemically speaking, is a salt. Not table salt necessarily, but a salt. It's the product, one of the products of an acid-base reaction is always a salt. The combination of a cation and an anion from your base and your acid. Okay, so now we need to balance it. Oops. There. Now sulfate has a 2- charge, sodium has a 1+ charge. Okay, now, and this is soluble. Right? So we're not going to have precipitate out of this one. All right, so this one should be easy to balance. Right, we need 2 sodiums over here, right? That gives us 2 sodiums, and we've already got 1 sulfate. Then if we have 2 hydrogens and 2 hydroxides, we get 2 waters. Right? 4 hydrogens, 1, 2, 1, 2, and 2 oxygens, 2 oxygens. So we're balanced. Okay. All right. Next, we want to reach the point where everything here is over there. So we're given 1 liter of 0.5 molar sulfuric acid. 1 liter of 0.50 molar, yes, sulfuric acid. The question is, how many moles of sodium hydroxide are required? Well, how many moles did we start with here? Yeah, 0.5 moles of sulfuric acid. Right, now we want to convert that H2SO4 to this one. So numerator, denominator cancels. The ratio is 2 of these for every one of those. So 1.00 moles of sodium hydroxide are required because that cancels and leaves us with this one. Okay. Here we go. Okay, that's our introduction to acid-base reactions. Next type of reaction is redox. Redox is short for oxidation reduction. So why don't we say oxred? Just doesn't sound right. Redox sounds better, but it means the same thing. Oxidation reduction. So if electrons have to be transferred in an oxidation reduction reaction, then we have to say something about how do we know electrons are being transferred? I'll give you an example. Say we have this synthesis reaction or combination reaction. Say we have sodium metal and chlorine gas. Right? Guess what that's going to make? Sodium chloride, table salt, right? There we go. Okay, so if we balance it, we put a 2 here and a 2 here, and we're balanced. Now, this is also an oxidation reduction reaction. How do we know? Because these atoms are neutral, right? All elements are neutral. These atoms are also neutral. There's no charge there. But this is an ionic compound. Like that. So how did they do that? Well, nonmetals love electrons. And metals are all too happy to give them up. So electrons from here traveled there. Actually, 2 of them. 1 for each sodium. And 1 ending up on each chlorine. That gives us a negative charge for the chlorines and a positive charge for the sodiums. Because each one lost 1 electron and each one gained 1 electron. So there we know that's an oxidation reduction reaction. And the rule of thumb is if you have an element on one side or the other, it doesn't matter, and it's in a compound on the other side of the arrow, you can guarantee that's oxidation reduction. For instance, if I say, let's see, rocket engine and liquid, well, by the time it gets to the rocket motor, it's gas. Hydrogen and oxygen. Remember the space shuttle when it took off? It had those 3 main engines, and that big orange tank was actually 2 tanks. One of them had liquid oxygen, and the other half of it had liquid oxygen, hydrogen and oxygen. And they mixed in the engines, and they produced water. Okay, let's see. 2 here and 2 there. So these are neutral. These are compound. Now, this is not an ionic compound, right? This is a covalent compound. But we use a technique called oxidation states to track the movement of electrons. And this one has an oxidation state of -2. This one has +1. Remember, they're not ions, but they allow us to bookkeep the electrons. Okay. But the rule of thumb still works. These are elements on this side. They're in a compound on that side. These are both oxidation reduction reactions. Okay. This is also a combustion reaction. Anytime you have oxygen as an element combined with something else to give you a compound, that's a combustion. Right? We can combust methane, which we're going to do today in our Bunsen burners. We can make methane combined with oxygen, and that would make carbon dioxide and water. That's not balanced, but that's what happens. Or we could do it with ammonia also. NH3 plus O2 yields NO2, I think, plus water. Does that work? I think that's right. But combustion, the hell of combustion is this free oxygen as a reactant. And they're always oxidation reduction reactions. Okay, here we have sodium and chlorine reacting to give you table salt. Oh, we are going to cover oxidation states. All right, so let's do that. You need some rules. Since we don't have ions to deal with, always, we don't always have ions. Sometimes we have covalent compounds where they're non-metal combinations. You don't have ions with those. Right, we learned that when we named compounds. We need rules, right, so that we can calculate the values for the other ones. So we always assume that an element in a reaction is always oxidation state 0. Oxidation state of a monatomic ion is the charge on the ion, like sodium +1, that's a +1 oxidation state. Oxygens in covalent compounds are assigned a -2 oxidation state, except for one situation. Come. Oxidation state for this one, let's use oxygen, that's 0. For this one is -2, okay? But for this one, hydrogen peroxide, oxidation state is -1. So here you have oxygen and hydrogens here, and here you have oxygen and hydrogen here and hydrogen here, and together -2. So each one has to be a -1. Okay, that's only for peroxides. Let's see, fluorine is always a -1 in a compound, like hydrogen fluoride. And hydrogens are nearly always +1. I think we left that one out. Hydrogens +1. If it's combined with a non-metal, hydrogen is going to be a +1. Here's a +1, here's a +1, +1. And here's a -2. Is it in there?
Fluorine.
Oh, I skipped over it. Yeah. +1 in covalent compounds. The exception to hydrogen is when it's combined with a metal. So this is hydrogen fluoride. If we say, how about let's do magnesium. That's magnesium hydride, right? It's the second position, so we have to end it with IDE. This is hydrogen fluoride. This is magnesium hydride. And this is, -1. Because magnesium is always 2+. Okay, so when it's combined with the metal, it's in the second position, it's the hydride, and it's a -1. Whereas in the first position, it's +1. Let's see. The sum of the oxidation states in a neutral compound must be 0. Can't have any imbalance. If the compound is neutral, all the oxidation states must add to 0. If you have a polyatomic ion, like this one, then the oxidation states have to add up to the charge. So in this case, oxygen would be -2, wouldn't it? We just said that. That means -6 total for all these oxygens, right? So what would nitrogen have to be to leave us with 1-? Plus 5 and the minus 6 is minus 1. Okay. That's an example of calculating. Nitrogen can be variable oxidation states. And if you look at your periodic table, you'll see down the side, the first one is going to be the charge in an ionic compound. So all of these are going to be minus 1, minus 1, minus 1, minus 1. But these are going to have several underneath them. And those are not charges. Those are oxidation states. Okay. I may have mentioned that earlier, but it probably didn't register because we hadn't got far enough. Okay. All right. So now we can use what we know to calculate the oxidation states of the various elements. And I'll say again, the reason we do that is so that we can track the movement of electrons. This is a bookkeeping scheme, oxidation states. It doesn't mean that they're ions. It just means that this is where we're plugging the electrons in so that we can account for all of them. Right? That's why I call it bookkeeping. K2CR207. K2CR207. We can approach this two different ways. If we're going to find out what the oxidation states of potassium and chromium are, well, potassium is an alkali metal. It's always plus 1. Right? I think that was one of the rules. Anyway, there's a plus 1. This is a minus 2. So if we just combine this one and this one, what do we have? Well, we have 2 pluses, right? 2 pluses, and we have a minus 14, don't we? Minus 14. So we combine them and we get a minus 12. That's what chromium has to balance. So these 2 chromiums have to be a plus 12 together. That means each one of them is a plus 6. That's what's known in the EPA as hexavalent chromium. I think hexavalent is the lesser of the toxic, isn't it? Trivalent is more toxic, I think. Anyway.
So if it's unspecified like chromium, if it's not specified, we just always use that.
You have to calculate it. Yes, you have to calculate it. Right? And chromium, if you look up, chromium was number 24. You look in this little box, it'll have several values. And the values for metals, they could be charges. All of them could be charges. But in this case, this is a polyatomic ion. Remember that one? Dichromate. Dichromate with a minus 2 charge. So is that true? 12 plus 12 and minus 14 is a minus 2 charge. So the dichromate ion is a minus 2 charge. These are covalently bound to each other. That's what polyatomic ions do. And they distribute the minus 2 charge over the entire group. But for our bookkeeping scheme, we can split them out and do the calculations. All right, how about the carbonate ion? Right? Okay, so we don't know what carbon is. We do know what oxygen is. So minus 2 times 3 is minus 6. We need to keep 2 of these minuses out for that charge. So really, we only have to balance a minus 4, don't we, with this one, which makes it a plus 4. And just check yourself. Plus 4 and a minus 6 is minus 2. Okay, MnO2. All right, we got another minus 2 here, so it's minus 4 total. This is a plus 4. PCl5. Now we have 2 nonmetals. And we don't have a rule for chlorine. We have one for fluorine, for fluoride. So what you have to do is decide, all right, how are we going to find out which is which? It's more likely that chlorine is going to have an oxidation state of minus 1 because it's a halogen. So if we say that, that makes this one plus 5. Okay. Sometimes you have to make that choice. When the rules don't cover it, you sort of have to expand the rules a little. And SF4, this one is fairly straightforward because we know that one is given a minus 1. which means -4. This one has to be a +4, oxidation state. Now, once we calculate the oxidation states, we can track electron movement, because on one side, the element might be one oxidation state, and on the other side, a different one. We know electrons have moved either from that element or to that element. We need to do an example. Well, there are the results. Okay. Definitions. Why do we call it redox or oxidation reduction? Definition. Oxidation is loss of electrons. Reduction is gain. That's why our acronym is oil rig. Oxidation is loss, reduction is gain. So anything that loses electrons has been oxidized. Anything that gains electrons has been reduced. And they always occur together. You can't have an oxidation without a reduction. So if something is oxidized, it caused the reduction of something else, which makes the oxidized species a reducing agent for the other one. See how that works? And vice versa. The one that was reduced is an oxidizing agent for the other one. Okay. Is this coming back? Okay. Which of the following are oxidation reduction reactions? Identify the oxidizing agent and the reducing agent. Okay. Am I coming down the home stretch?
Not one.
Okay. Let's be quick about it then. If we have zinc, let's see, A is zinc plus, that's a solid. I guess I better put the phases in here. +2 hydrochloric acid, right? Aqueous means we name it as an acid. And then we get these compounds. And there are only a few reactions where you can deduce the products, right? Those double displacement reactions, they're easy to do the products. Acid-base reactions, they're easy to do the products. But some of these other reactions, yeah, we need to give you the products before you can work with them. Okay, so this one's 0, -1 +1. This one's -1 because that one has to be +1. That means this one is -1 and this one is +2. Right? And this one is 0. So what I do is I use tie lines. So if I go from zinc here to zinc here, something happened. 0 to +1 +2. So what happened? How does it go from a 0 to a +2? Remember, you can't move protons. It had to lose 2 electrons. So we had a loss of 2 electrons per zinc. Where else? Chlorine didn't change. Hydrogen did change. Right? Hydrogen gained 1 electron per hydrogen times 2 equals 2 electrons gained. Okay. That's another thing. The number of electrons lost must equal the number gained. Always. No exceptions. So this one was a loss of electrons is oxidation. That makes this one the reducing agent. And this one was reduced, which makes it the oxidizing agent. Okay, so this one is an oxidation reduction reaction, and we've identified the reducing agents and the oxidizing agents. The next one I think if I drew it out, we can show that chromium is +6 on both sides. We already did Cr2O7. That chromium is +6. Right? We do the oxygens are all -2. Right? They're all -2. Just look at them. -2 for dichromate, -2 for hydroxide, because -2 and +1 for hydrogen is -1. Right? And on the other side, Cr04. 4 times -2 is -8. We hold out 2 negatives for the charge. That's a 9 at -6. We got 1 chromium +6. So chromium didn't change. And water is +1 and -2. So we had no oxidation state changes in B. That's not a oxidation reduction reaction. But the last one, I want to show you this one. I wanted to throw that one out quick. This one is 2. All right. Is that a copper 1 or a copper 2 chloride? It's a copper 1 chloride. -1 +1. And we're going to take that one and we're going to end up with this one. This is a +2. So we did get a change. All right. This copper tie line was an oxidation loss. 1 electron per coupling. But we also go to this one. That's 0. This was a gain of 1 electron per coupling. That seems strange, right? You got this compound going 2 directions at once, right? It's schizophrenic. Actually, it's not. There are 2 of them. One of them went that way, the other one went that way. So 1 copper lost an electron to the other molecule's copper to go that direction. Right? One of them went this way, one of them went that way. This is called a disproportionation reaction. And it's commonly used in the mining industry and smelting industry to isolate and remove copper. I don't think this would be very efficient for a wholesale harvesting of copper from an ore, because you'd lose half of it. So if they do this, then they're going to have to take this one and do something else to get that copper back. Okay, so those 2 are oxidation reduction reactions. So this is what I do. You follow the same procedure. You write your compounds correctly. You write you balance the equation. Then you do your oxidation states. And if you have a change in oxidation state from one side to the other on any of the elements, then you draw your tie lines and say which one's oxidized and which one's reduced. And in order to balance the equation, oxidation reductions reactions, some of them will respond to direct budget method for balancing. Some of them are resistant, and they work best if you balance the electrons first. Then you take the equation and finish the budget method. Right? It gives you a new starting point. Once you got the electrons balanced, then the rest of it tends to fall into place. And we'll go through one of those in the review session. Okay, show you how to do that. Let's see. If we have solid zinc and hydrochloric acid, that's always going to produce hydrogen gas and zinc 2 chloride. This is the reaction. That's the unbalanced equation. If we do the oxidation states, there's 0, +2, -1, 0. So we see that zinc changed and hydrogen changed. Right? Draw the tie lines. That's an oxidation of zinc and a reduction of hydrogen. Okay. Now to balance it, we need 2 hydrogens. So we put a coefficient in front of the HCl, and we don't need 2 in front of the hydrogen because it's already got 2. All right, so we just draw our tie lines again. And we put a 2 in front of the HCl, and lo and behold, it balances the equation with just 1 coefficient. Okay. Okay, there's the finished product. And you can check yourself. Right? Just say, how many of each one do you have? And you should come out. Oh, 2 in front of the chloride. I forgot that one. Yeah, you need a 2 in front of the chloride also.
The only time we're gonna balance electrons like that is in redox.
Yes.
Okay.
If it's not a redox, it ought to respond very well to the budget method. Yep. Okay. I'm a couple minutes over. So the lab officially starts at 2 o'clock. So you got time for a short break. We didn't talk about the lab in detail. I hope you had a chance to look at the video in Brightspace. It would give you kind of an orientation of what we're going to do in there. It's really simple. We're just getting oriented to the lab, and we're going to work with a burner. We're going to play with fire first, and then we're going to do some measurements. We're going to do length measurements. We're going to do mass measurements, volume measurements, and record those results on the hard copy, and that's what you turn in. But you don't have to turn it in today. You can work with it and turn it in the next time we come in for a lab, which will be probably 2 weeks. Let's see, there's that one. Yeah, we skip next Tuesday and we go to the Tuesday after that. Next Tuesday, we have an exam. So Thursday, we're going to do a review for that exam. I may give you some introductory remarks when we're in there. If you've never worked with lab equipment before, then I need to hold things up and tell you what they are, because the method may not be explanatory. Like, what's an Erlenmeyer flask? I don't know. Is it this thing, this long thing with a base on it and markings on the side? No, that's a graduated cylinder. Erlenmeyer flask looks like a cone. Okay, things like that. If you've been in before, you can, snooze for a few minutes. And I would recommend wearing gloves. We're not going to have any hazardous chemicals today, but we do have glassware. We do have hot things, and a layer of nitrile glove. Right, if you just accidentally grab something that's hot, then you'll feel just a little tingle before it burns. You can let it go. Right, I'd rather have broken glass than burned flesh. Okay, so we can reconvene in the lab. Everybody knows what the lab is. Last door on the left toward the parking lot is the lab. I'll have to go unlock it, actually.